Okay, let's go ahead and begin. Hi, everyone. Welcome to our second EGI webinar of the fall season. Today, we're going to be hearing from Dr. Palash Panja. He is a research assistant professor here at the University of Utah and a research scientist here at EGI. Okay, he will be presenting today, and we will have some time for questions and answers after the presentation, so be sure to stick around. You can either raise your hand after, or you can put them in the chat box if you have a question for him. Once this presentation is done, I will download it and we will put it on YouTube, so if you miss it or know anyone who wants to listen to it, it'll be available. Okay, Dr. Panja. It is all yours.
Yeah, thank you, Jenny, for the introduction. My name is Palash Panja. So today's webinar, EGI webinar topic is integrated data analytics of US tight oil plays, production performance, sweet spot, and recovery trends. So here is the outline of my talk. I have divided it into 4 sections. First part, I will discuss about our data sources and pre-processing. Then I will show you some example of our EGI Shale Smart web application. Then I'll show you some example results using that app, some data analytics. And finally, I will have some concluding remarks. Let's start with data sources and pre-processing. So data is very scarce, mainly for oil and gas. So we have gathered data from drilling info. We have academic license. Mainly we gathered production data with minimum completion data like lateral length, location, and TVD, true vertical depth. For more complicated or more detailed completion data, we have used frac focus. From that, we can use like completion data like proppant, number of fractures, amount of water used. Then other sources also we have used like State Service, the Railroad Commission of Texas, Oil and Gas Division, North Dakota. So those are the main data sources for this study. So before we directly use this production data downloaded from all these sources, we need to do the pre-processing because of there are many reasons. There are outliers, there are not correct, sometimes not correct data also. Firstly, there are 2 types of data we have collected. One is called time series data. That is, it has monthly data, like for 2 years of production, it has like each month from the starting from month 1 to 24 month, we have all the data like production data. And we have cumulative data also. That means like single row for one well, we have like cumulative production, cumulative oil, or cumulative associated or dissolved gas for oil. So after gathering those data, we filtered because we cannot use those data, all the data. So first filter we applied was we selected only oil wells because it's more, our studies focused on oil wells. So we only selected oil wells. Then we selected horizontal wells. Because this is the tight formation, we assume most of the tight formation maybe probably like more close to 100% tight formation is horizontal, come from horizontal wells. And of course, we selected another thing. We selected those wells which have 24 months of production data. We selected this way because to get the stabilized production data. Otherwise, if we take very early production data, it will be like biased in the analysis because early production is normally higher than the later production. So we make sure that each well at least have it has 24 months of production. But some cases it is 36 months for, I will tell you later, like for time series data or UR calculation. And another thing we have noticed that's kind of outlier. When we selected horizontal wells, some wells, actually many wells, are assigned horizontal wells, although they have lateral lengths of like 100 feet, 500 feet. We thought that my colleague is here also in this. He's also attending, Rasul Sarkavi. We discuss it. We thought that maybe it's like little bit diverted wells at the end, and those are assigned at horizontal wells. So to avoid those things, we selected at least minimum 1,000 feet horizontal length. And because we are dealing with thousands of wells, we don't do it manually. So it's all sets in Python code. That's why you have to set up all the filters in the code, and then we run the code for thousands of wells. So we have different sets of data downloaded from different time periods, like early 20s, then late 24, 25, early 25. So these are some tentative numbers that of data we are analyzing in this application. Like you can see, we have selected vast areas in the USA from Anadarko, then next 2 to 5 base formations are from Permian Basin, like Delaware and Midland. Then also use Gulf Coast basins, West and Central, Williston Basin for Bakken, Powder River or DJ Basin for Niobrara, and Fourth Worth for Barnett Shale. And if you see the oil counts, we have around 78,000 oils from all of these tight formations. And next challenge we had after data filtering is merging the data, or how do you unify production data with completion data like from frac focus or other log data from other sources. So of course we use well API number, and well API number is unique number provided to each well. So we use Python code to merge those data. But sometimes we don't, if you don't use completion data, then we don't need to merge. Sometimes if you need completion data, then merging will reduce the number of wells significantly, because not all production wells have the completion data from frac focus. That way we lose some number of wells actually when we merge. Then second challenge was how to compare all the oils on a same scale, because some oils have like 20 years of production, some oils have like 3 years of productions. Some oils are 10,000 feet laterally, some oils are like 1,000 feet, 5,000 feet laterally. So to compare them on a same scale, we normalized. We have given them name, like it's called normalized cumulative production, or NCP. It is calculated by dividing cumulative oil production by oil length and the duration of production. And this units of NCP is barrel, stock tank barrel divided by feet, foot, or month. For all analysis, we use this NCP. Let's talk about the Shale Smart. We have developed a Shale Smart web app at AGI. It has the ArcGIS background map. It has all the ArcGIS layers, and over that, we have applied our backend and front-end application. Backend, we have many Python coding, where data are analyzed, automatically filtered, and they are like then superimposed on this map. Then front end, we have very good many tools. On the right hand side, you can see there are two tools are shown. One is Voronoi or Kriging, and then cross plots. And in Voronoi, we have tools like you can select any region in that wherever data is available. You select some region, you select some thousands of wells, then you can do Voronoi or Kiriging. And also you can do for those same wells, the cross plots. We have many cross plots I will discuss in a few minutes. So in this analytical tool, we have different capabilities, like 4 of them I have shown on this slide. First one is like reservoir characterization. We can interpret a log or some production data using material balance type, unique material balance method we have developed at EGI. For that, we need log data. For material balance, we need production data and PVT and initial condition. Using those things, we have some empirical relationships, some machine learning tool inside that inside this app in the backend, and we can calculate TOC, porosity, permeability for material balance, and water saturation. Next one is a field development application. As I discussed in this previous slide, that we have a Voronoi diagram. We can do we can select the well location, and then we can select any parameters like permeability, EOR, or any cumulative production. Then we can apply this thing. Another feature of this application is that you can put one dot anywhere. Then this distribution they will redistribute again in the region wise and properties wise. Then you will understand what will be the effect of the new wells in this region, effect on the production, effect of the other average properties. Next one is this cross plot type analysis, and we have more than 25 plots. It's a different plots from different angles to try to understand what's going on underground. I will discuss more in the later. And then we have different surrogate models using like ANN. Then for time series, we have long short-term memory. It is called LSTM machine learning algorithm. And we have other XGBoost. For using those model, trained model, already we have trained model for some input parameters like matrix permeability, rock compressibility, initial GOR, initial pressure. You can predict the oil recovery or oil cumulative production or time series production. So various analysis and visualization plots, you can see the 4 examples, like reservoir. In the left figure, we have plotted reservoir depth versus location, but the third parameter in the bottom, the bar diagram, color diagram, third parameter is the depth. So you can easily visualize the depth of all the wells it's a Eagleford. It's dipping in the southeast region, as you see the yellowish color. And the northwest side, it's more like shallower oil wells. And plot is like longitude versus latitude. And also another thing you can notice, in the right-hand side of the figure and the top of the figure, we have histogram also. So you can do mean, median, or any other standard statistical analysis, quantitative analysis also. And the middle figure, it's a kind of sweet spot. You can plot any parameters versus any parameters. Like in this plot, we have in the y-axis TVD, true vertical depth, and x-axis is normalized production. That's NCP. And the third parameter, we use the oil counts, and similar, it has some histogram also, right-hand side and top. And you can see the red spot. Red spot shows that where most wells are drilled. So it's around like 11,000 feet oil is deep, and where normalized production was around 0.5. So that's the place where people or operators or the oil companies drilled most of the oils. Then impact of lateral length also, we this type of plot we chose on the x-axis, which is like lateral length, and y-axis normalized production, and we have the histogram distribution. We have more detailed discussion later. And technological impact, that means when oil was completed and started producing. So if you plot like 2008 or 2006 to 2018, you can see the normally production increases. And our hypothesis is that it's due to better completion, better fracturing job, and maybe better production strategy. So I will quickly go through like how Voronoi works in our web app. So basically, you can draw any arbitrary diagram, arbitrary boundary, and that's shown in the first picture. And before that, you can select any properties. For example, I selected here like permeability, millidarcy. Although these millidarcy values are high for tight formation, these for example. And location, it's basically location in the X and Y axis, latitude and longitude. So after selecting that thing, you apply the Voronoi and kriging. So you can see that color map, it do the kriging, then applying the Voronoi theory, it will distribute the area among the wells. Each well has its own area. And next, you just can average the properties of that area. So in the right-hand side figure, you can see it's a single color for each area. That means it's the average properties of that color. So it will give you lot of information like average permeability, average porosity of that around that well, around that drainage area. And also you can calculate the area of that Voronoi. So that will give you also the drainage area for that thing. Of course, it's a theoretical drainage area, but it's a more scientific way to divide the region among the wells. And you can calculate original oil in place, recovery factor, UR, and again, I discussed in the previous slides, like you can place a new wells, it will distribute again, and it will give you the new picture. So let's talk about data analytics. So for data analytics, let me check my microphone is working. Yeah. So we have many publication already. We are working on this thing around like 10, 15 years. A lot of students, researchers worked in this Shale Smart project, and we have published a lot of papers in journals and conference. So for example, in these plots, we have normalized production versus depth. And in the third parameter in the bar diagram, it's the first month GOR. And it is like there are eight main tight formation in the USA, from the Austin Chalk in the south to extreme north, Bakken, then Permian Basin. Let's talk about the first figure, the Austin Chalk Gulf Coast West. And you see that it's the TVT in the y-axis and normalized production in the x-axis. And if you see the TVT distribution on the right-hand side, it's a bimodal. So it shows the hidden feature or hidden information that the most of the wells are completed in two regions. One is like 6 to 7,000 feet. Another is like 10 to 12,000 feet. And then if you talk about like now other figure, like figure number 7, Wolfcamp Delaware, you can see there are almost like single mode in the distribution, like figure number 7, bottom third, Wolfcamp Delaware. You can say depth of that most oil completed was around like 11,000, close to 12,000 feet, and it's a sharp peak. And it reveals that the most oil resides at that depth. So for each figure, for each place, you can find some information, important information, which can you apply later for new oil drilling. So observation number 1. So you can see most of the time we see that the production is like bell-shaped. Production sweet spot, as I discussed. Although it has some window, oil window. And in the right-hand figure, we have overlapped the thermal gradient or temperature range with the depth, and right-hand side, we have shown that bell shape production window or the completion window. And you can see upper hand, the 4,000, 6,000 feet, it's not, oil is not supposed to be there. We assume that it's probably migrated oil from the bottom layer. And then 4,000 to 6,000 to 12,000 feet is the ideal location for at least this type of formation. And it's the oil prone zone because it's a perfect for thermal maturity. It's between like 60 to 120 degrees centigrade. And below that depth, below that 12,000 feet, it's the over matured, it's the gas zone. And it has minimum oil amount. So let's talk about the another type of plot. Like it's a normalized production versus initial GOR. The first one was normalized production versus TVD. It is the initial GOR. So initial GOR means gas oil ratio. The initial means the first month we have considered. How the first month GOR affects the production in the long term. So and also we have one frontier line. It was drawn to obtain the maximum limit in the frontier. And then frontier line is always like inverse relationship with the first month GOR, that when first month GOR is increasing, the production is declining. But if you see the distribution, like first talk about the first figure, Austin Chalk, Gulf Coast West, you can see it has the median GOR, first month GOR is around like only 172. It's too low actually for one oil well. And initial GOR is important because it's a kind of dissolved gas in oil. It helps producing oil in many ways. First way is when it dissolves in the oil, it reduces the viscosity and increases the mobility of oil. And in later stage, when dissolved gas comes out of the oil and it's a free gas over the oil, it helps to sustain the reservoir pressure. But too much gas is not good because then it competes with oil in the mobility. It has higher mobility, it will suppress the oil production and you will get more gas. So that's why the optimum initial GOR is good, dissolved GOR, but too much GOR is bad. And too low is also bad. So in the Austin Chalk, it's a too low, like 172 median. And that's why you can see on the right-hand side, the distribution that normalized production also really low, 0.29. Now let's compare again my ideal play, Wolfcamp Delaware, the 7th picture and 3rd from the bottom. And you can see the initial GOR and from the distribution on the top, the initial GOR is like around median is like 1600, and it's almost like ideal. And for NCP is almost like median is 0.93 and compared to like 0.29 in Austin Chalk. So that's the conclusion from this slide, that optimum initial GOR is better for long-term normalized, long-term production. And there is another remarks, similar remarks to that previous observation, is that there is, of course, gas window, oil window, and a shallow reservoir with oil migrated from the deeper oil levels. Best producing zone is located between like 6,000 to like 12,000 feet because it's the thermally matured and good press. It has good pressure. Sometimes oil is matured, but if reservoir does not have enough pressure, it cannot sustain the production for a long time. And we have seen in many tight formation, the oils died after like few years, 2-3 years, even not even like 10, it reaches 10 years. So it's a similar conclusion, and it's the pay zone with moderate initial GOR is good for better performance in the long term, but other factors also contributes like permeability and reservoir pressure. Those are also other factors other than the initial GOR. So some other plots we have this, for examples, you can see each column is one property plot and each row is one formation. So we have like here 1, 3, 3, 9 formations, and at the bottom their color legends are provided, and there are 4 columns, 4 properties: lateral length, true vertical depth, first month GOR, and production duration. And you can plot for any properties using our Shale Smart, this type of plots. This type of plot is very useful because if you can draw a line vertically for any column, then you can compare all this formation at once. So that's the usefulness of this type of plots. And yeah, we have some comments from lateral lengths. You can see few wells have very high lateral lengths, median lateral lengths compared to others. Like for example, Wolfcamp Midland has very long lateral lengths. Median is like 7,000 feet, and few others are like very short length. True vertical lengths also, some wells are very deeper, some wells are shallower, and you can compare. Like first figure, you can see it's like 9,600 feet median. Wolfcamp Delaware has like 11,000 median. And so you can do similar analysis for any properties using our app. So let's talk about our third topic, like recovery trends. Basically, we'll discuss about the EUR, estimated ultimate recovery. And we have published few papers. 2 papers are shown here. They are published in URTech, I think 2024, and this year 2025. If you want to know details, please download, or we can share those papers with you. So brief theory. So for tight formation, there are different types of ARFs modeling, and for tight formation, ARFs hyperbolic declining, it's called AHD. And those models are developed in 1945 and is used in tight formation. Normally B value in this equation is restricted between 0 to 1. That's fraction basically. So we have historical data from time series data, and then we fit those data to get those B and DI, these 2 parameters. Once we have B and DI, and we do it in Python, we do it for thousands of wells, tens of thousands of wells automatically. And when we run the Python code, it saves those B and QI and DI automatically. And using those values, later, in the next stage, we calculate EUR, estimated ultimate recovery. So definition of estimated ultimate recovery is that the amount of cumulative oil until economic rate. Until after that, we cannot produce at economic way. So there are 2 ways we do. Normally, when flow rate drops below certain limit, we have set 120 barrel per month. If flow rate drops 120 barrel below per month, then we stop counting. And second one, another one is like 30 years of production. Sometimes in the theoretical, the flat portion keep going actually. It does not decline significantly. So that's why we stopped it after 30 years for most of the oil, except Bakken. Bakken, we applied 60 years because we have seen the trend. There are many wells more than 30 years. So we use that. So whichever criteria occurred first, we stop the simulation or stop the Python code or for that well. So after getting those EUR from each oil, we have distribution of that and we ranked them accordingly. And these plots, basically the y-axis is the estimated ultimate recovery in 1,000, M is 1,000 barrel, and we have ranked them main 8 formation, we rank them 1 to 8. And you can see the first one, Wolfcamp Delaware in Permian Basin, has almost 400,000 barrel EUR expected from this type of from this formation. Bakken is the rank number 2. It has median of 332,000 barrel. And Eagleford is interesting. It's like half of actually Wolfcamp Delaware. So they are almost like close basin. Eagleford in the right-hand side or the eastern side in the Texas, and Wolfcamp is the western side of Texas and New Mexico. But their EUR is 400 versus 200, almost half in median. And similarly, Wolfcamp Midland, the last figure is the figure number 8. You can see it's the same basin, Permian Basin, but different formation, different depth. One is Delaware, one is Midland, but their EUR is so different. Wolfcamp Midland has almost like 199 median, 99,000 barrel. It's like 1/4 of Wolfcamp Delaware production. It's surprising how the formation, completion, depth, oil maturity affects the ultimate recovery. So MSTB is 1,000 stock tank barrel. So an MM is million. So M stands for, normally in the mathematics of this notation, is 1,000. And MM is like 1,000, 1,000 is 10 to the 6. So I'm answering the question in the chat. So for better comparison, we have the bar diagram just to compare, show you again. Already I discussed, like first one, rank number 1 is 400 versus Midland is the middle, almost like 98.5, and Eagleford is 204, and Austin Chalk close to Eagleford, but Austin Chalk is like 132. So there are many reasons, like some reasons are given on this slide, like some deep burial, high thermal maturity for Wolfcamp. That's why it is number 1. Maybe it has advanced stimulation because Permian Basin recently has seen a lot of activities for stimulation techniques, and probably they are using very advanced technology. Then Bakken and Bone Spring. Bakken is known for liquid production, and probably it has hybrid lithologies. It's sandstone sandwich between dolomite siltstone sandwich between shale, black shale, and it has significant depth also, which helps producing oil generation. Eagleford is actually mixed formation. It has in the south or northwest has oil, then slowly it's a condensate in the middle, and then southeast it has gas, and it has all 3 types of production, and it's a mixed. It has a lot of heterogeneity, lithological heterogeneity, and the hydrocarbon heterogeneity. And then shallower and gas-prone place like Niobrara, Wolfcamp, Midland has very low oil accordingly because it is gas-prone and some oils are very shallow. And we tried to also understand what's the connection between the TVD, true vertical depth versus the median. It's a positively correlated, directly proportional, but one formation, the Woodford, is like outlier. It has high TVD, like 12,000, almost the end of the oil zone, like 6,000 to 12,000. That's why maybe the one reason. And it has very low EUR, like 76,000. And another reason, maybe it's a basinal settings. It's different variable phases. and poor source and reservoir connections. So another thing I want to discuss, it's the longevity of wells. So it is commonly said that wells in tight formations are not like wells in conventional. Conventional oil wells like last 40 years, more than 30 years, and has recovery factor like 35%, 40%. On contrary, the tight formation recovery factor is sometimes like most of the time less than 10%. And lifetime is like 3 years, 4 years. So that's why from the EOR study, when we extend the EOR study, the curve in the Earth's curve, and when we stop that terminal, when we apply that terminal condition, either 120 barrel per month, or when it reaches the 30 years or 60 years. Actually, we are surprised that most of the plays, we did not reach 30 years. You can see the vertical line in the middle, that's the 30 years, 360 months. We did not reach that criteria. Before that, the production dropped below 120 barrel per month. And Marcellus is the worst. It's like 7 years almost. After 7, it's a median value. Even many wells are, of course, more than 7 years and less than 7 years. Median value is like almost 7 years. And if you consider 30 years, we are not producing the rest of 23 years. The wells are abundant. But best performing is Bakken. It almost reaches 30 years median. It has more than 30 years some wells. And second best is Wolfcamp Delaware. Then from the bottom I am talking about, Bakken has almost 30 years, 362 months. Delaware is like 338, almost 30 years, like 27 or something years. Then Bone Spring, Delaware also has good longevity of wells. These are projected, by the way, using the EOR. We are projecting the lifespan using that curve. So this is the good learning from this study, that we can expect the longevity of oil in each place. So we have other publications related to this, all the shale studies. There are numerous publications. So let's do the concluding remarks. So as I discussed in this webinar, that Shale Smart we have developed at EGI is an analytical and modeling tool where we have integrated log, production data and completion data for performance analysis, forecasting, to select the restimulation candidate in wells. We have some other advanced analysis like neighboring wells. I haven't discussed in this webinar, but they are in our app. Then we can select the sweet spot mapping for any properties. We have a Voronoi kriging that will give you a spatial and some empirical modeling also for drainage area. We have NPI, or it's a NPC, the normalized production index, EOR. And from the data, we can understand by doing the reverse engineering. We have one paper on that. We can understand actually petroleum system. Just by doing all these plots, we can understand where petroleum systems reside in the reservoir also. And we can infer many information from this type of data. And from data related thing, I will say like Wolfcamp Delaware, Bakken, and Bone Spring are the winner in this tight formation. They have a huge production, huge EOR also, more than 2,000. Wolfcamp Delaware has 400, and other, these three have more than 200,000 barrel EOR. Most probably they are the deep burial, high maturity, and optimized completion and production. And finally, we have several researchers and students. They are working continuously to improve this app. Any remarks, any suggestion will help us to develop this app for future. And if you have your own data, you can upload those data in our system, and you can do all same analysis what we are doing with our data repository right now. So if you have any project, please contact us for future collaboration. Thank you so much for listening, for your attention. Now, if you have any question in the chat box, or we can talk directly, I will be happy to answer those questions. We have almost 20 minutes to discuss. I have slide number, so if you can mention slide number, then I can go to those slides. So one question I have from Luke is that, does the longevity analysis include the gas production economics? We did not. Longevity analysis is purely theoretical, based on the EUR analysis, estimated ultimate recovery, using Earth's hyperbolic decline. We did not include the EUR economics actually. Actually, we are writing one paper for science. Dr. Rasul Sarkavi in this webinar, we are writing one paper for science. We are going to add economics, but we did not think about the gas economy, but oil economy. And thinking about the Marcellus and other gas-prone plays, oil economics being negatively affected by using oil only. I agree with you, Luke. But normally, gas price is low. If it is liquidative, I think that will add more interest. That will show more interest in this low oil zone with huge gas production. GOR is transient. Yes, GOR is gas oil ratio normally increases with time. Initial gas oil ratio is the minimum one from my reservoir engineering knowledge, I can say. So Henry, your question is GOR is transient and it varies with choke size also, correct? Flow rate, PVT effects, gas migration. Try using oil gravity also. Okay, oil API gravity. Yes, we have API gravity from frac focus and some production data, I think. Production data, we can do that. Good size. Yes, thank you, Henry. So Luke, yes, thank you to you too. In future, to look for to use the ShellSmart tool. Yeah, we can. If you have meeting, we can show you online directly demonstration. I did not take the risk to show you online. Normally, online demonstration is always like there will be some glitch, a problem. So I did not take that risk. Yes, we can show you the tool. If you have any question, you can. I think you can start the mic. Okay, 1 minute. My speaker is off. I think Sydney, sorry.
Need to unmute somebody.
1 minute. I have some technical problem now. Yes, Jenny, can you talk?
Yeah, I can talk.
Yeah. Sydney, please go ahead. My speaker went off, the external speaker. I did not notice that. Yeah. I cannot hear Sydney, I think. Oh.
Yeah, I can't either.
Can I ask a question? This is Sid Green.
Mhm.
Yes, I can hear Sydney.
Okay.
So I can hear, but
have you looked
very
at,
low.
or maybe you are looking at now, at water production to do the same kind of analysis, see what associated water production is?
I did not get you, but you are talking about the associated water production, right? Yes, we have associated water production, and we have some analysis with the water production also for like completion. Yes, we have, uh,
You know,
said-
associated water production is so big
Mhm.
that, you know, it's of interest too, is that how does that affect things?
Yes, yeah. I know the conventional, the water cut normally at the end of life goes like more than 95%. And in tight formation also, we have some water production. We have some analysis with water also. I did not show here for the sake of time. We have that data set, water production, associated gas production. Do you want to do some particular analysis?
Very nice presentation.
Okay, any other question, remarks? Rasul, do you have any remarks? Rasul is the co-researcher with me who we developed together this Shale Smart.
Rasul had a class. He had
Oh,
to
he
run.
left. I think he left then. Yeah, he joined and he left.
Well, thank you everyone for joining us. Palash, do you have
Yeah, thank
anything
you.
else?
Yeah, thank you everyone for attending this webinar. If you have any question, you can reach me directly. You just email me and we can talk offline.
Okay,
Thanks,
great.
Balash.
Yeah, thank you so much. Yeah.
Thank
Yeah,
you, everyone.
nice. Really good. Thanks.
And again, I will put this recording up on YouTube in the next couple of days. Thank you.